Hi everyone, I'm Takumi, Machine Learning Engineer at the Google Advanced Solutions Lab. This is the second half of the image captioning section. If you haven't seen the first half, I recommend checking it at first. And in this video, I'm going to walk you through the entire code notebook to help you understand how to create a very simple generative model. All the setup information is written in the ASL GitHub repository. You can find the link in the slide or in the description below this video. After setting up the Vertex AI Workbench environment and cloning the repo following the instruction, you can find the image captioning notebook under ASL ML Immersion, Notebooks, and Multimodal Solutions. Here you go, you can find image captioning.ipython notebook. So please open this file. And here you can see all the process and instructions to build and use an image captioning model, which we discussed in the previous video. Let's take a look from the first cell. In the first cell, of course, we install all the dependencies, including TensorFlow Keras. And here you can find TensorFlow Keras layers and installing all the layers we need for image captioning model, including GRU, add layer, attention layer, or dense layer, embedding layer, layer normalization layer. So let's run one by one. And in the next cell, we define some hyperparameters, including vocabulary size, which means how many vocabularies we're going to use for image captioning. Or you can find feature extractor, which means what kind of model we want to use in encoder model. So in this case, as we discussed in the previous video, we are specifying Inception ResNet v2, which is very classical CNN-based model. And all the definitions below, image height, width, channel, and feature shape is coming from the definition of the Inception ResNet v2. And especially this feature shape, 881,536, is the shape this Inception ResNet v2 produce. So let's define in this way. Cool. So in the next cell, we're going to load the data from TFDS, which means TensorFlow datasets. So TensorFlow datasets host this caption dataset in this name, Coco Captions, so we can specify this name and load the data. And after loading data, we can pass some preprocessing function, get image label, which is defined here, get image label, and here you can find some preprocessing, very basic preprocessing, including changing the size of the image or the changing the scale of the image and returning image tensor and the caption at the same time. So let's run in the same way. And let's take a look at some of the example. Here we can see four random example, and each pair of image and text makes sense to me. So white plate with a toasted sandwich, chips and fries for this image, and another caption for another image. And we have a lot of image. So if you want to see the other example, you can run this cell again and you will see another example. So let's move on. So since we have text data, we need to pre-process the text data in kind of standard way. So in this cell, we add start and end special tokens, which we discussed in the slide as well. So by adding this, so we can handle this token as a kind of special sign. The start token means the special token, that means the beginning of the sentence. And in the same way, the end token means the end of the sentence. So we're going to add these things in the same way, train ds.map and pass this function name. Let's move on. And this is very important pre-processing. So now we have text data, caption data. So we're going to create tokenizer. So by creating tokenizer, we can tokenize word like star token or cat or dog to some index. In TensorFlow, it is very easy. You can just use this text vectorization module and you can call by passing all the data, all the caption data to this text vectorization layer. So it takes some time, around 5 minutes in my environment. So let's wait until it finishes. Now it finished. Now let's try this tokenizer by passing some sample sentence. Star token, this is the sentence, end token. So now you can see it is tokenized in this way. And also here you can find a lot of paddings. By changing this max caption length, you can control the length of this padding. Okay, but in this case, we are specifying 64, so all the captions will be padded in this way until this max caption length. And in the same way, you can see the behavior of this tokenizer. This is very useful. Once you create, you can apply this tokenizer in different captions and convert text data to the word tokens. And it's nice to create converters at this point. So here you can find string lookup layer, and creating the converter from word to index and also index to word. So we're going to use these modules later. So this is quite useful. And then we can create a final data set. So this is a very important part. So we have train ds. We're going to add additional create ds function, this function. And as you can see, it returns image tensor caption. So this is the tuple. Image tensor will go to encoder and caption will go to the decoder. And also we are creating target, which is label. And in this function, you can find this target is created from caption by the shifting this caption in one word. Okay, by doing so, we're gonna create a shifted caption, which means the next word. Okay, and we're gonna utilize this for target. Okay, so let's define and apply this function and create a batch and specify the batch size, and everything is ready. So let's take a look at the sum of the data set. Here you go. So you can find the image in this shape and caption in this shape and label in the same shape as caption because we are just shifting and also we are padding the shifted part with 0 value. Looks nice. So the next part is model. Most of the model code is already explained in the previous video, so I'm going to go through very quickly. But if you are not very familiar with that, very confident with that, then you can go back to the previous slide and check what is going on inside encoder and decoder. So here in this video, so let's quickly run these things. So this is encoder, and as you can see, we are just applying inception resonant v2 to image data. And please note that in this case, we are freezing the most of the parts of this CNN because we don't need to train this model. Basically, this kind of the backbone is pre-trained by using huge data set, in this case, ImageNet data set. So of course, if you want to the train fine tune again, it is possible. But in this case, we want to just preserve the weights pre-trained. So next, let's move on to the decoder. It is a bit complex as we discussed, and here you can find a lot of instruction about the attention layer and also the steps of the decoder, which we discussed in the previous video. And here you can find the definitions. So here you can find embedding layer to create word embedding, and first GRU layer, and attention layer, add layer, layer normalization, and final dense layer. So let's define in this way. So model looks like this. Embedding layer, GRU, attention, add, layer normalization, and dense. And it has so many parameters. After defining decoder and also encoder, we can create final model, TF-Keras model, and define inputs and output. And as you can see, it has two inputs. Image input goes to encoder, and word input goes to the decoder. And output should be decoder output. Now model is ready, but before running training, we need to define loss function as usual. So in terms of the loss, our model is basically a classification model since the decoder generate a lot of probabilities for each class, each word class, each vocabularies. So we can use sparse categorical cross entropy as usual for the classification problem. But in this case, our data is padded, so it has a lot of the zero values and a lot of the meaningless values. So we want to remove that part. So in order to do so, we are defining this custom loss function. And then everything is ready. So let's compile the model. And we can run training. And in terms of the training, it takes 15 minutes to 20 minutes with one GPU, one T4 GPUs to train one epoch. So if you want to add additional epochs, it's okay. You can do that. And I think you can get the slightly better result. But epoch, if one epoch is enough to just to check how it works. So let's just keep it as one and run training. And let's wait 15 to 20 minutes until it finishes the training. Now training is done, so let's use it for captioning. But before that, we need to rebuild the decoder for inference in order to control the GRU state manually as we talked in the previous video. So in this cell, by reusing the trained layers, we are creating a model for inference. So here you can find trained decoder GRU, trained decoder attention, and so on. And compared to the training model, we are adding GRU state to its IOs. For inputs, we are adding GRU state inputs, and for output, we are adding GRU state as output. So by doing so, we can control the GRU state in the inference loop. Okay, so let's generate text with this custom inference loop function. We already discussed what kind of the component it should have in the previous video, but let's review very briefly. So first, we initialize GRU states, in this case just initialize with 0 vector simply. And then we get image and preprocess the image and pass it to encoder. Of course, the train encoder. And we can get the image features. And before passing it to a decoder, so we also initialize this start token as the first word. And then we are going to repeat this for loop again and again and generate text one by one. So step looks like this, calling decoder, of course, and it returns a lot of predictions, a lot of the word probabilities. So there are so many ways to pick up the actual word, the final selection from the list of a lot of word probabilities. But in this case, we are pulling the word kind of stochastically to introduce some randomness. So it is these lines of codes are doing that, and eventually picking up some words and the bringing it back to bring it back to the word from the word token by using the tokenizer and appending to the list. So eventually we should get some captions. So let's take a look at the result. So define this function and let's call it. So here you can see a caption samples for this image. So this sample image is located in this directly, just passing this baseball.jpg, and it returns 5 captions. It looks like this: a baseball player standing next to the bat, a catcher in a field playing baseball, or something like that. It is not grammatically perfect, but still you can see it is generating the text, generating multiple text, and generating the meaningful text. And also we can see our model is capturing important informations like baseball or catcher or a man standing next to another man or baseball field or something like that. So still, it's not perfect, but it is generating very meaningful text. It's very surprising, isn't it? So the model is very simple. We are just stacking encoder and decoder and passing the image data to encoder, and the decoder generated captions one by one, but in autoregressive way. So just by stacking this, so we can create this kind of the very small generative model. Again, currently there are so many generative large language models out there. Of course, they have more complex and larger network and train a much larger dataset. But the architecture may look similar to this simple model. Thank you so much for watching this video. I hope you enjoyed. If you like this presentation, you'll find more in our ASL GitHub repository with 90 plus machine learning notebooks. If you find it useful, please don't forget to start the repository.